Right now, at this very moment, something is falling into a black hole. From our perspective, it has been falling for decades. It will continue falling forever. It will never reach the bottom. But from the perspective of that falling object, it has already crossed the point of no return, been torn apart by gravity, and ceased to exist, all in a fraction of a second. Both perspectives are correct. Both are happening simultaneously, and the implications destroy everything we thought we understood about the nature of time itself. What if time isn't a universal constant flowing equally for everyone? What if the universe doesn't have a single now? What if the past, present, and future exist simultaneously, and we're simply trapped in our limited perspective, unable to see the full picture? Black holes force us to confront these possibilities. They're not just objects in space, they're rifts in the fabric of time itself, places where past and future become meaningless, where the universe reveals its most closely guarded secret, that time, as we experience it, is an illusion. Today, we journey through evidence that challenges everything we know about the universe's most fundamental dimension. We'll follow matter to the edge of existence. We'll watch stars freeze mid-collapse. We'll discover why black holes may be windows into the true nature of reality itself.
Tonight, you can simply listen.
In 1916, just months after Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild did something extraordinary. He was serving on the Russian front during World War I, calculating artillery trajectories by day. But at night, by candlelight in frozen trenches, he solved Einstein's equations. What he found should have been impossible. Schwarzschild discovered that if you compressed enough mass into a small enough space, you would create a region where gravity becomes so intense that nothing, not even light, could escape. The mathematics predicted a boundary, a point of no return, where the fabric of space-time itself would warp so severely that it would essentially rip. But here's what nobody expected. At this boundary, time itself would stop, not slow down gradually, not pause temporarily, stop completely, forever. Einstein himself rejected the idea. He called it a mathematical curiosity, an artifact of the equations that couldn't possibly exist in the real universe. For decades, most physicists agreed. These Schwarzschild singularities were treated as interesting thought experiments, nothing more. Then, in 1964, everything changed. A team of rocket-borne X-ray detectors detected something inexplicable coming from the constellation Cygnus. The source, designated Cygnus X1, was emitting more X-rays than entire galaxies. The energy output was staggering, equivalent to the sun's entire lifetime energy production compressed into a single second, repeating over and over. But it wasn't just the power that puzzled astronomers, it was the pattern. The X-rays flickered on timescales of milliseconds. That meant the source couldn't be larger than a few hundred kilometers across, far too small to be a star, yet far too energetic to be anything scientists could explain. Optical observations revealed a blue supergiant, HDE 226868, with mass equivalent to 30 suns. But something invisible was orbiting it, something so massive it made the supergiant star wobble. Calculations showed the invisible companion had a mass of at least 15 solar masses compressed into a space smaller than Manhattan. The evidence pointed to a genuine Schwarzschild singularity, a black hole, a place where stars go to die and where time itself goes to end. But accepting black holes as real objects created an immediate paradox, one that would haunt physics for decades and remains unresolved today. Here's the problem. According to Einstein's equations, as matter falls toward a black hole, time dilation becomes more and more extreme. To a distant observer watching from safety, the falling matter appears to slow down. The closer it gets to the event horizon, the point of no return, the slower it moves. At the event horizon itself, time dilation becomes infinite. The falling matter doesn't just slow down, it freezes completely. From our perspective, watching from a safe distance, nothing ever actually crosses the event horizon. We would watch a star collapse, see it compress smaller and smaller, watch its surface approach the critical boundary, and then watch it freeze at that precise moment, suspended in time forever. This is why physicist John Wheeler initially called them frozen stars. And this is where it gets genuinely strange. From the perspective of the falling matter, nothing unusual happens at the event horizon. Time flows normally. The matter crosses the boundary in finite time and continues falling inward toward the singularity at the center. So which perspective is correct? Does the matter freeze forever at the boundary, or does it fall through? The answer, and this might be the most unsettling part, is both. The matter exists in a superposition of states. It is simultaneously frozen at the event horizon for eternity and already destroyed at the singularity. Past, present, and future happen at once. The sequential flow of time we experience breaks down completely. But the evidence forces us to confront an uncomfortable possibility that the smooth, consistent flow of time we take for granted is merely a local phenomenon, a comforting illusion that falls apart when we look at the universe's most extreme environments. The frozen stars are trying to tell us something profound about reality itself.
Eventually, in 1971, astronomers discovered something extraordinary about Cygnus X1. Spectral lines that should have been visible simply weren't there. Light was being redshifted, stretched to longer wavelengths so dramatically that it was disappearing from the visible spectrum entirely. This wasn't just Doppler shift from motion. This was gravitational redshift, light climbing out of a gravity well so deep that photons lost most of their energy in the escape attempt. But here's the remarkable part. The degree of redshift corresponded exactly to predictions for matter orbiting just outside a black hole's event horizon. Matter that close experiences time running at roughly 30% the speed of normal time. Every second that passes for that matter, 3 seconds pass for us. The Event Horizon Telescope observations of M87's black hole in 2019 revealed this effect in stunning detail. The glowing ring of matter around the black hole shows asymmetric brightness. One side appears brighter than the other. This isn't because more matter exists on that side. It's because of time dilation. The bright side is moving toward us. Matter there experiences relativistic beaming. Time dilation and Doppler shift combine to make the light appear more energetic and concentrated. The dim side is moving away, experiencing the opposite effect. We're literally watching time flow at different rates in different parts of the accretion disk. Scientists measured this precisely. Matter on the bright side is experiencing time at 85% normal rate. Matter on the opposite side, 68% normal rate. These aren't small effects. These are dramatic distortions of time itself, visible across 50 million light years. Since the 1990s, astronomers have been tracking stars orbiting the center of our galaxy using ever more precise instruments. The target, Sagittarius A*, a radio source at the galactic core. One star, designated S2, has been observed for over 25 years.
Its orbit is extraordinary. It sweeps around the galactic center once every 16 years, reaching speeds of 7,650 kilometers per second at closest approach. That's 2.5% the speed of light. At those velocities, relativistic effects become impossible to ignore. During its closest approach in 2018, something remarkable happened. The star's light was redshifted by exactly the amount predicted by general relativity for an object passing through the intense gravitational field of a black hole with mass equivalent to 4 million solar suns. But here's what makes this evidence so compelling. We can see that the star is orbiting nothing visible. The mass at the center of our galaxy, this 4 million solar mass object, emits no light. It occupies a space smaller than Mercury's orbit around our Sun. The only explanation consistent with the evidence is a supermassive black hole. What we're watching is a star experiencing time at a different rate than we do. During its 2018 approach, for every second that passed for S2, roughly 1.0002 seconds passed for us. Over the course of its orbit, S2 lost about 30 minutes compared to clocks on Earth. The star is orbiting a frozen point in time, a place where billions of years ago matter collapsed inward and from our perspective is still collapsing, frozen at the moment before it crossed the event horizon. Here's where the evidence becomes truly puzzling. Astronomers have found stellar mass black holes, those formed from collapsed stars, ranging from 5 to 50 times the mass of our Sun. We've also found supermassive black holes, those at galactic centers, ranging from millions to billions of solar masses. But intermediate mass black holes, those between 100 and 100,000 solar masses, are mysteriously rare. In 2020, gravitational wave detectors finally caught one, a collision between two black holes with masses of 85 and 65 solar masses, creating an intermediate black hole of 142 solar masses. The signal, designated GW190521, revealed something unexpected. The merger produced a black hole that rang like a struck bell, emitting gravitational waves at specific frequencies determined by its mass and spin. But the ringing died away faster than predicted, much faster. This suggests that the newly formed black hole settled into its final state more quickly than standard models predicted. It's as if time inside the event horizon was flowing faster than the equations suggested, or as if the very concept of duration becomes meaningless at those scales. But this represents just one piece of a much larger puzzle that challenges our understanding of how time itself operates near these extreme objects.
Years later, in 1974, Stephen Hawking made a discovery that shook theoretical physics to its core. Using quantum field theory near black hole event horizons, he calculated that black holes should emit radiation, now called Hawking radiation, and eventually evaporate completely. The calculation seemed straightforward, but it created an impossible paradox. Quantum mechanics demands that information cannot be destroyed. If you know the exact quantum state of a system at one moment, you can theoretically calculate its state at any other moment. Information is preserved. But if a black hole evaporates via Hawking radiation, what happens to the information about everything that fell in? The radiation is thermal, random, carrying no information about what created the black hole. The information seems to simply vanish from the universe. This shouldn't be possible. It violates the fundamental laws of quantum mechanics. Yet the mathematics is clear. The most remarkable thing about this paradox, it's fundamentally a paradox about time. The question isn't just where does the information go, it's when does it exist? If matter is frozen at the event horizon from our perspective, but has already fallen in from its own perspective, in which timeline does the information reside? Recent calculations suggest a possible resolution.
The information might be encoded on the event horizon itself, in subtle correlations within the Hawking radiation that would only become apparent over timescales longer than the universe's current age. The information isn't destroyed, it's time-locked, accessible only to observers who could wait trillions of years. As these ideas developed, in 2012, physicists proposed something that sounded like science fiction but emerged from rigorous calculations: the black hole firewall. Here's the setup. According to classical general relativity, nothing special happens at the event horizon. It's just a mathematical boundary. An astronaut falling through wouldn't feel anything unusual, wouldn't even know they'd crossed it until they tried, futilely, to escape. But when you add quantum mechanics to the picture, something disturbing emerges. To preserve information, quantum correlations must exist between particles inside and outside the horizon. But quantum mechanics limits how many correlations a single particle can maintain. The math suggests that maintaining these correlations requires breaking other quantum connections violently. The result, the event horizon might not be a smooth, empty boundary. It might be a seething wall of high-energy particles, a firewall that would instantly incinerate anything trying to cross it. This creates a paradox. General relativity says crossing the event horizon is smooth and uneventful. Quantum mechanics suggests it's a violent, destructive process. Both theories have been tested extensively and proven accurate, yet they give contradictory predictions. The discrepancy reveals something profound. We don't understand what happens to matter and time at the event horizon. Our best theories break down completely. The frozen star phenomenon isn't just an interesting relativistic effect, it's a signpost marking the boundary where our understanding of physics fails. Perhaps the strangest implication comes from considering black hole formation itself. When a massive star collapses, the core compresses rapidly. From the perspective of the collapsing matter, it crosses its own Schwarzschild radius and continues falling inward to the singularity in finite time, usually less than a second. But from our perspective, watching from outside, the surface never quite reaches the Schwarzschild radius. It approaches asymptotically, getting closer and closer but never arriving. The star appears to freeze at the moment of collapse, its surface hovering just above the event horizon. This means that from our reference frame, the singularity at the center of a black hole doesn't exist yet. It's still forming. It will always be forming. The collapse is frozen mid-process. But we see the effects of the singularity. We observe black holes pulling on stars, bending light, generating X-rays from infalling matter. We're seeing the effects of something that from our perspective hasn't finished forming yet. This is more than a paradox about time. It's evidence that our concept of causation itself breaks down. Effects precede causes. The future influences the past. The universe contains objects that simultaneously exist and don't exist depending on your frame of reference. The evidence extends beyond physics into the realm of philosophy, forcing us to reconsider what we mean by existence itself.
The universe's strange behavior of time near black holes leads to a radical conclusion. Time might not flow at all. Consider the block universe model, supported by many physicists, including Einstein himself. In this view, past, present, and future all exist simultaneously. The universe is a four-dimensional structure where time is just another dimension, like length, width, and height. The passage of time, the sense that now moves forward, is an illusion created by our consciousness. Black holes provide evidence for this model. The fact that infalling matter is simultaneously frozen at the horizon from one perspective and destroyed at the singularity from another perspective makes sense if both moments exist equally. There is no single now for the universe. There are only different perspectives moving through the block of space-time. Physicist Carlo Rovelli at the Centre de Physique Théorique in Marseille puts it this way: the difference between past, present, and future is only a stubbornly persistent illusion. Black holes don't just warp space, they reveal time's apparent flow is a property of our limited perspective, not a fundamental feature of reality. This forces us to reconsider fundamental assumptions about causation, free will, and the nature of existence itself. If all moments exist equally, if time doesn't actually flow, then the universe isn't evolving. It simply is, complete and eternal, and we're experiencing it slice by slice. Not everyone accepts the block universe model. Alternative interpretations attempt to preserve time's flow while explaining black hole behavior. The complementarity principle, proposed by Leonard Susskind at Stanford, suggests that different observers experience genuinely different realities near black holes. From outside, matter remains frozen at the horizon. From inside, it falls through. Both descriptions are complete and accurate from their respective frames of reference. They can never be compared directly because no signal can travel from inside the horizon to outside, so the contradiction never manifests. This interpretation preserves time's flow, but at a cost. It suggests reality itself is observer-dependent. There is no objective truth about what happens at the event horizon, only truths relative to specific observers. Another approach, loop quantum gravity, developed by researchers including Abhay Ashtekar at Pennsylvania State University, suggests that quantum effects prevent singularities from forming. In this model, the collapse halts just before the singularity forms, creating a quantum bounce that might eventually reverse the black hole's formation. Time continues flowing, but on quantum scales that modify general relativity's predictions. Recent work by researchers at the Perimeter Institute suggests yet another possibility. Black holes might be fuzzballs, extended quantum objects without well-defined event horizons. In this picture, what we call a black hole is actually a quantum superposition of many possible configurations. Time doesn't stop because there is no sharp boundary where time dilation becomes infinite. Each interpretation attempts to resolve the paradoxes while preserving different aspects of our understanding. But all of them agree on one thing: black holes reveal that time, as we experience it, cannot be the whole story.
The Event Horizon Telescope made history in 2019 by imaging M87's black hole. But that was just the beginning. The network is expanding, adding new radio telescopes and improving sensitivity. Within the next 5 years, we'll have movies of matter orbiting black holes, watching it spiral inward in real time. These observations will test general relativity at unprecedented precision. We'll measure how light bends near the event horizon with enough accuracy to detect deviations that could reveal quantum gravitational effects. We'll watch matter approach the point where time dilation becomes extreme and see if it behaves exactly as Einstein predicted, or if something unexpected happens. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers. These cataclysmic collisions involve black holes millions or billions of times more massive than our Sun, warping space-time so severely that the waves remain detectable across the entire universe. Most remarkably, LISA will detect the ring-down phase of these mergers, the period when the newly formed black hole settles into its final state. This ring-down encodes information about the black hole's interior structure. If black holes are truly described by general relativity, the ring-down will match specific predictions. If quantum effects or exotic physics modify the structure, we'll see deviations. We're about to test whether black holes truly are the frozen stars predicted by Einstein's equations, or whether there's something even stranger.
Black holes represent laboratories for physics that can't be studied any other way. At the singularity, matter compresses to infinite density. Quantum effects and gravitational effects become equally important. This is the realm of quantum gravity, the still undiscovered theory that would unify quantum mechanics and general relativity. String theory, one approach to quantum gravity, makes specific predictions about black holes. In string theory, particles are actually tiny vibrating strings. Black holes would be states where strings become highly entangled and collapsed. The theory predicts subtle modifications to Hawking radiation and the structure of the event horizon. Recent breakthroughs suggest these modifications might be detectable. In 2020, theorists calculated that string theory predicts specific patterns in gravitational waves from black hole mergers, patterns different from general relativity's predictions by just 1 to 2%, but potentially measurable with next-generation detectors. Loop quantum mechanics makes different predictions. In this framework, space itself is quantized, made of discrete units at the smallest scales. Black hole interiors would show quantum bounces rather than singularities. The predictions differ from string theory by observable amounts. Within the next 2 decades, gravitational wave observations might tell us which approach to quantum gravity is correct by watching how black holes behave in their most extreme moments. These aren't abstract questions disconnected from human concerns. Understanding time's nature affects how we think about ourselves, our choices, our place in the universe. If the block universe model is correct, if past, present, and future exist equally, then in some sense, you exist at every moment of your life simultaneously. The you reading this now exists eternally in this moment. The child you were exists eternally in those moments. The elder you'll become exists eternally in future moments. You are not progressing through time. You are time, a 4-dimensional structure extended through the temporal dimension. This doesn't eliminate meaning or choice. Your decisions still determine which path through the block universe you follow. But it suggests that every moment you experience is permanent, eternal, woven into the fabric of reality itself. Black holes are teachers. They're showing us that the universe is stranger, more unified, more fundamentally interconnected than our everyday experience suggests. Time isn't separate from space. Past isn't separate from future. Reality isn't divided into independent pieces. It's a single unified structure that we experience in fragments. The frozen stars are mirrors, reflecting back to us the limitations of our perspective and inviting us to see beyond them.
At the center of every black hole, the equations predict a singularity, a point where density becomes infinite, where space-time curvature becomes infinite, where the mathematics breaks down completely. But does the singularity actually exist? From our external perspective, matter never finishes collapsing. The singularity is always in the future, always forming but never formed. Yet from the perspective of infalling matter, the singularity is reached in finite time, and the matter ceases to exist. Physicist Roger Penrose proposed cosmic censorship, the idea that singularities are always hidden behind event horizons, preventing us from ever observing them directly. This seems to be true. We've never detected a naked singularity, a place where the equations break down that we could actually study. But why? What mechanism ensures singularities remain hidden? Is it a fundamental law of physics, or merely an accident of the solutions we found? The most profound implications emerge when we consider that the Big Bang itself was a singularity, a moment when the entire observable universe existed at a point, with infinite density and temperature. If black hole singularities don't actually exist as mathematical pathologies, but rather as quantum structures we don't yet understand, then perhaps the Big Bang singularity also isn't what we think. Maybe time didn't begin at the Big Bang. Maybe something existed before, a previous universe, a quantum foam, a higher dimensional structure. The singularity might not be a beginning, but a transition, a moment of extreme change rather than creation from nothing. Black holes might be windows into the universe's birth, structures that recreate in miniature the conditions present at the cosmos's earliest moment. Perhaps the strangest implication comes from information theory. In the 1990s, physicists realized something extraordinary. The maximum amount of information that can be stored in a region of space is proportional not to the volume, but to the surface area of that region. This is called the holographic principle. It suggests that three-dimensional reality is actually encoded on a two-dimensional surface, like a hologram. Black holes provide the clearest evidence for this principle. Jacob Bekenstein and Stephen Hawking showed that black hole entropy, the amount of information a black hole contains, is proportional to the event horizon's surface area, not its volume. A black hole with twice the radius has 4 times the entropy, not 8 times. This shouldn't make sense. If black holes were normal three-dimensional objects, entropy should scale with volume, but they don't follow that pattern. They behave as if all their information is encoded on their two-dimensional surface. Juan Maldacena at the Institute for Advanced Study proved a remarkable result in 1997. A theory of quantum gravity in a higher dimensional space is mathematically equivalent to a quantum field theory on the boundary of that space. The three-dimensional reality we experience might literally be a projection from a two-dimensional surface. If this is true, if the holographic principle is fundamental, then space itself might be an illusion. The three-dimensional universe we inhabit might be a kind of interference pattern, information encoded on a distant boundary and projected inward. Time might be similarly emergent. Multiple researchers have proposed that time itself arises from quantum entanglement, from the way information is distributed and correlated across the holographic boundary. Time wouldn't be fundamental, but would emerge from deeper structures we don't yet understand. Black holes are telling us that reality's dimensionality, its spatial extent, even time's flow, all of these might be emergent properties rather than fundamental features. The universe might be profoundly different from anything we can directly perceive.
The ultimate mystery. Despite decades of research and remarkable technological advances, the core mystery remains unsolved. We don't know what happens at the event horizon. We don't know if singularities exist. We don't know where information goes when black holes evaporate. Most fundamentally, we don't know what time is. Is it real or illusory? Does it flow, or is that sensation an artifact of consciousness? Does it exist independently or emerge from quantum correlations? Is the present moment special, or do all moments exist equally? Black holes force these questions into focus because they're places where time breaks. They're laboratories showing us that our intuitions fail, that the comfortable assumptions we make about reality don't hold in extreme conditions. And extreme conditions reveal truth. When you push systems to their limits, you discover what's fundamental and what's contingent, what's real and what's approximate. The answers might come from unexpected directions. Recent experiments with quantum entanglement suggest that space and time might emerge from entanglement patterns. If you have quantum particles that are sufficiently entangled, they create something like a spatial connection between them. Add more entanglement in specific patterns, and you might generate something like time. This suggests reality is fundamentally quantum information, patterns of correlation and entanglement, and space and time are just useful descriptions that emerge at large scales, like how temperature emerges from molecular motion. If this is correct, then black holes aren't destroying information, they're reorganizing it. The frozen star isn't frozen in time, it's existing in a regime where our macroscopic concept of time fails to apply, but where deeper quantum structures continue evolving according to laws we're only beginning to understand. The universe might be vastly stranger than we imagine, but it's also comprehensible. Every mystery we solve reveals new mysteries, but they're mysteries we can investigate, questions we can formulate and test. The frozen stars watch us, silent and patient, waiting for us to understand the message they've been broadcasting since the universe began. That time is not what it seems, that reality is unified in ways we're only beginning to grasp, that the cosmos is more beautiful and more bizarre than our ancestors dared imagine.
The Planck scale barrier. At a scale of 10 to the minus 35 meters, the Planck length, quantum gravitational effects become dominant. This is the smallest possible meaningful length in physics. At this scale, space-time itself becomes grainy, discrete, quantum. Space is no longer smooth, but made of individual units, like pixels on a screen, but infinitely smaller. In loop quantum gravity, when collapsing matter reaches these densities, around 10 to the 96th kilograms per cubic meter, quantum pressure creates a bounce. The collapse reverses, creating what some researchers call a black hole to white hole transition. Think of it like a quantum trampoline. Matter falls inward, compressing until it reaches Planck density. At that point, quantum effects create enormous repulsive pressure, not from any known force, but from the quantum geometry of space-time itself refusing to compress further. The matter rebounds. From the outside, this transition would take infinite time. We'd never see it. The black hole would appear eternal, slowly evaporating via Hawking radiation. But from the perspective of matter inside, the bounce happens quickly, perhaps in microseconds of internal time. Matter compresses to Planck density, then rebounds explosively. Where general relativity predicts a singularity, infinite density, infinite curvature, mathematics breaking down, quantum gravity predicts a bounce. The singularity is replaced by a moment of maximum compression followed by expansion. If this is correct, black holes are temporary structures. Given enough time, vastly more than the current age of the universe, perhaps 10 to the 100 years or more, they would eventually explode, releasing their contents as white holes. White holes are the time reverse of black holes, regions of space-time from which matter and light can only exit, never enter. Time continues flowing in this picture, but on scales that make the universe's 13.8 billion year age seem like an eye blink. A stellar mass black hole would take longer than 10 to the 67 years to complete its black hole to white hole transition, a duration with no meaningful comparison in human experience.
String theory's predictions. String theory offers yet another perspective. In this framework, the fundamental constituents of reality aren't point particles, but tiny one-dimensional strings of energy vibrating in 10 or 11 dimensions. Different vibration patterns create different particles. An electron is one vibration pattern, a quark is another. Black holes in string theory would be states where strings become highly entangled and collapsed into an incredibly complex configuration. The theory predicts subtle modifications to Hawking radiation and the structure of the event horizon. Most remarkably, string theory suggests that black holes have entropy proportional to their horizon area because the event horizon is literally made of strings, Planck-length strings woven together in an astronomically complex pattern. Each unique arrangement of strings represents one microstate of the black hole. Counting those microstates gives the entropy. In 2020, researchers at the Institute for Advanced Study, including Juan Maldacena, performed calculations showing that string theory predicts specific patterns in gravitational waves from black hole mergers, subtle oscillations called echoes that would appear milliseconds after the main merger signal. These echoes would differ from general relativity's predictions by just 1 to 2% in amplitude, but they'd have distinctive frequency patterns. If detected, these echoes would be smoking gun evidence for string theory. They would prove that black hole horizons have quantum structure, that they're not the smooth mathematical surfaces predicted by classical general relativity, but quantum objects with internal complexity. Next-generation gravitational wave detectors being planned, like the Einstein Telescope in Europe and Cosmic Explorer in the United States, should be sensitive enough to detect these echoes if they exist. Within 2 decades, we might have experimental evidence for or against string theory drawn from black hole observations.
The holographic universe. The holographic principle emerged from studying black hole thermodynamics, but its implications extend far beyond black holes. It might describe the entire universe. Here's the radical claim. Everything happening in our three-dimensional universe, every particle, every force, every event, can be completely described by information encoded on a two-dimensional surface far away, like a hologram projecting a three-dimensional image. The evidence comes from black holes. Jacob Bekenstein, working in the early 1970s, realized that black holes must have entropy. When matter falls into a black hole, the matter's entropy seems to disappear from our universe, but the second law of thermodynamics says entropy can't decrease. Therefore, black holes must carry entropy themselves. Bekenstein calculated that black hole entropy should be proportional to the event horizon's surface area. Stephen Hawking later calculated the exact constant. Black hole entropy equals 1/4 of the horizon area in Planck units. This is bizarre. Normal objects have entropy proportional to volume. A box twice as wide has 8 times the volume and can hold 8 times as many molecules in 8 times as many configurations, but a black hole twice as wide has only 4 times the entropy. It's as if all the information about what's inside a black hole is stored on its surface, not in its volume, as if the three-dimensional interior is a projection of two-dimensional information on the horizon. In 1993, Gerard 't Hooft and Leonard Susskind independently proposed that this might be universal. Perhaps all of three-dimensional space works this way. Perhaps we're living in a hologram. The mathematical proof. Juan Maldacena proved a specific version of this in 1997. He showed that a particular theory of quantum gravity in 5-dimensional anti-de Sitter space, a space with negative curvature, is mathematically equivalent to a 4-dimensional quantum field theory on the boundary of that space. This ADS-CFT correspondence, anti-de Sitter conformal field theory, is a precise duality. Every calculation in the 5-dimensional gravity theory has a corresponding calculation in the 4-dimensional field theory. Every object, every process, every measurement in one theory maps to something in the other theory. They're two descriptions of the same reality. Our universe isn't anti-de Sitter space. It has positive curvature, not negative, but the ADS-CFT correspondence proves that holographic descriptions are mathematically possible and internally consistent. It opens the door to the possibility that our universe is holographic. If true, space itself is an illusion. The 3 dimensions we move through, left, right, forward, backward, up, down, are emergent properties, like how temperature emerges from molecular motion. The fundamental reality is 2-dimensional information on a distant boundary, and 3-dimensional space is how we experience that information.
Multiple researchers have taken this further, proposing that time itself emerges from quantum entanglement. Mark van Ramsdonk at the University of British Columbia showed in 2010 that in ADS/CFT, quantum entanglement in the boundary theory corresponds to spatial connections in the bulk theory. More entanglement means more connection through space. Less entanglement means space fragmenting, disconnecting. If you could somehow remove all entanglement, space would fall apart into disconnected pieces. This suggests time might work similarly. The flow of time might be the subjective experience of increasing entanglement or changing entanglement patterns. What we call earlier might correspond to states with certain entanglement structures. What we call later might correspond to states with different entanglement structures. In this view, time doesn't flow, it's a dimension organizing different entanglement configurations. Our consciousness moves through these configurations, and we interpret that as time passing. But fundamentally, all moments exist equally, distinguished only by their entanglement patterns. Black holes fit naturally into this picture. They create maximal entanglement. The event horizon is the most entangled possible boundary. Time behaves strangely near black holes because entanglement patterns become extreme there. The frozen star phenomenon reflects not time stopping, but entanglement structure becoming so complex that our usual temporal concepts fail.
In the 1980s, Alan Guth proposed that the early universe underwent inflation, exponential expansion driven by a scalar field. This solved several cosmological problems: why the universe is so uniform, why it's geometrically flat, why we don't see magnetic monopoles. But André Linde and others realized that inflation, once started, might never completely end. In most regions, inflation stops and normal expansion begins, creating pockets of normal spacetime, universes like ours. But in some regions, quantum fluctuations keep inflation going. Those regions continue expanding exponentially, spawning more pocket universes. This eternal inflation creates an infinite multiverse, countless bubble universes, each with potentially different physical properties, different constants of nature, different laws of physics. Black holes as universe creators. Some theoretical work suggests black holes might be connected to this process. When matter collapses past the event horizon, instead of forming a singularity, it might trigger a new inflationary expansion, but one that's disconnected from our space-time. From outside, we see a black hole. From inside, there's a big bang. A new universe buds off, with its own space, its own time, its own history, stretching into its own future. Lee Smolin at the Perimeter Institute developed this into a theory called cosmological natural selection in the 1990s. If black holes create baby universes, and if those baby universes inherit slightly modified physical constants from their parents, then universes that produce many black holes would spawn many offspring. Over many generations, the multiverse would become dominated by universes optimized for black hole production. And what produces black holes? Stars. And what produces stars? Matter, gravity, nuclear fusion, the same processes that allow planets, chemistry, and life. This would explain why physical constants seem fine-tuned for life, not because of design, but because of evolution. Universes with random constants mostly don't produce stars or black holes, so they don't reproduce. Universes with constants like ours produce lots of stars and black holes, so they reproduce abundantly. We exist in a universe fine-tuned for black holes, and life is a side effect. We began with a paradox: matter falling into a black hole, simultaneously frozen at the event horizon for eternity and destroyed at the singularity in finite time. We've journeyed through evidence from across the cosmos,
We've watched stars orbit invisible masses, seen light redshifted by extreme gravity, tracked matter as time dilates to near stopping. We've explored the mathematics of general relativity and quantum mechanics, discovered paradoxes that challenge our understanding of information, causation, and reality itself. And we've reached a transformed understanding. Time is not the universal flowing river we experience in our everyday lives. It's something stranger, a dimension woven into space-time's fabric, warped by mass and energy, potentially emergent from deeper quantum structures. Black holes are more than collapsed stars. They're windows into the universe's deepest nature. They're laboratories revealing physics we can't study anywhere else. They're mirrors reflecting our assumptions back at us and forcing us to question everything we thought we knew. Current scientific consensus acknowledges that we stand at a frontier. General relativity and quantum mechanics both work remarkably well in their domains, but give contradictory predictions about black holes. The solution, quantum gravity, remains undiscovered, but we're closer than ever before. New observations, more powerful detectors, and theoretical breakthroughs are converging. Within our lifetimes, we might answer questions that have puzzled humanity for generations. We might discover that time is an illusion, or we might find that it's more fundamental than we imagined. We might learn that black holes are quantum fuzzballs, or frozen stars, or something we haven't yet conceived. The journey continues. Every black hole we observe, every gravitational wave we detect, every theoretical calculation we complete brings us closer to understanding. The universe is revealing its secrets, slowly, carefully, but inevitably. And perhaps the most inspiring part, we're here to witness it. In a universe billions of years old and trillions of light years across, we evolved the capacity to ask these questions, develop the mathematics to explore them, and build the instruments to test our answers. The frozen stars are waiting. The mysteries are deep. The quest for understanding continues.
The universe is vast. The mysteries are endless, but we keep looking. We keep questioning. We keep discovering. And that makes all the difference.